All right, well, these definite intervals, a to b of an f of x dx is what we're wanting to figure out. Now, by definition, this is our definition of the integral. Limit as n goes to infinity of this summation. And I'm using right-hand endpoints here to kind of make it a little easier on ourselves, because you can use whatever endpoints you want. But any way you go, it's going to be kind of complicated. So here our function is just x squared, right? F of x is x squared. And so we're talking, looking at the handout there, so that equals then, the first thing I did on that handout is just say, well, so I'm using right-hand endpoints. This is f of x, so f of x of I would be x of I squared times delta x. Now, by formula, delta x is b minus a over n. And so x of 1, we're starting at a, so x of 1 is the next one over. We would take a plus the delta x, and so that would be a plus b minus a over n. Unfortunately, a and b here are not, we're just doing them in general here too, but that's okay. So anyway, is that okay? A plus delta x would just be a plus this b minus a over n. X of 2 then would be a plus b minus a over n plus another b minus a over n. So I'm going to have a plus 2 b minus a over n's. And then x of 3, put it down here, is a plus 3 times b minus a over n, because you're just going to add another b minus a over n to that. So I think we can get the point here. X of I is going to be a plus whatever the I is times b minus a over n. All right? Because x of 2 is a plus 2, b minus a over x of 3 is, all right? That's not that big of a jump, right? Well, if I plug that in for x of I then, right there, I get the integral a to b, so this is line 1 now. I get b minus, integral a to b of x squared dx is now the limit as n goes to infinity of x of I squared times delta x, but delta, I'm sorry, that's my x of I, so get everything put on here. So that's the x of I, so it'd be a plus I times b minus a over n squared times delta x, which delta x is b minus a over n. So I'm just plugging in those things. That's line 1. All right, so line 2, I've got everything spelled out there. It's just integral from a to b. Oh. Okay, so in line 2, what did I do? Well, in line 2, this is where the properties that we went over last time come in handy. Since this summation is the index is I, that doesn't involve I, so that's just a constant, so I can pull that out front. So that's what I did on line 2, pull that out front. And so on line 3, what am I going to do for line 3? Well, on line 3, I have b minus a over n times the summation of, okay, so in line 3, I believe what I'm going to do here is just square that out. Write that out twice and square it out, so you get a squared plus, and you can full it out, whatever, but cut to the chase, it's just going to be 2 times a times I times b minus a over n plus, you're going to have I squared times b minus a over n squared. Just pulling that out. for line 3. Line 4, well, I've got it written out. Let's see what I did. I've got the limit as n goes to infinity, b minus a over n time. Okay, so look at what I did on line 4. I've got three things in this summation now. And by whatever property it was, if I've got three things in my sum, I can separate those all into separate summations. So that's what I did. I got the summation of the a squareds plus the summation of this 2ai times b minus a over n. Oh, I'll put the I at the back there. Plus the summation of b minus a over n squared times I squared with the I squared. Flip-flop those. So I just did those as separate summations, right? All right, what did I do on line 5? I got that written out too. On line 5, limit as n goes to infinity. All right, so that's b minus a over n times then summation a squared. I didn't do anything with that. Plus some 2a times b minus a over n times the summation of I. Well, the same thing I did in a previous, this step right here. This right here, that doesn't depend at all on the I. This is I equals 1 to n. I'm not writing that, but it's on the paper. That doesn't at all depend on I. So I can bring it out. That's all I did for that. And then the same thing goes here. I can bring this out because that doesn't have I in it. And then just have the summation of the I squared. Okay? That was line 5. Line 6. Okay, so I got to do something here. Well, on line 6, I can use my properties again. This is just, since that's I equals 1 to n, the summation, that's just the summation of your constant. Remember we said the summation of a constant is just c times n. So this is just a squared times n. Now what about the summation of the i's? Well, the summation of the i's from that property that we went over was n times n plus 1 over 2, wasn't it? That's what the summation of the i's were. So I can plug that in for the summation of the i's. And then I had an I squared formula as well. It's just b minus a over n squared times the summation of the I squareds. Well, the summation of the I squareds was, let's see if I remember, n times n plus 1 times 2n plus 1 divided by 6. That was another property that we talked about. Okay. Let's go over here. So number 7, line 7. I think I've got it, I've got it written down. So let's see what I did. Is that okay? Any problem or concern with what I got for line 6? Is everybody good with that? I'm just using the formulas that we talked about. Okay, so line 7. We'll have the limit as n goes to infinity. We got it on paper. It's b minus a over n. Okay, so what did I do for line 7? On line 7, I just took this b minus a over n and multiplied it by all 3 parts. So I have b minus a over n times n a squared n. And then when I multiply the b minus a over n times this, well, it'll just make that a squared. So I have 2a times b minus a over n squared times n plus 1 over 2. And then times this, and then b minus a over n times that will just make that a cube. Okay. We're getting there. All right, so that was line 7. Line 8. Limit as n goes to infinity. I've got this one on the paper too, so let's see what. Okay. So in line 8, I just did some canceling. The n's cancel, so I have b minus a times a squared. That's all that's left here. The 2's cancel here, and then I put it as a, and then I did b minus a squared over n squared. I did those separately squared times your, and I multiplied those out. There's different ways you can do it. That's what I did, and then b minus a cubed over n cubed. Nothing cancels here. Oh, I went ahead and started multiplying these out. So that's 2n squared, 3n plus 1 divided by 6. I just multiplied those two binomials for line 8. Then line 9, let's see what I did there. See why I wrote all this, so you wouldn't have to write it. Just let me talk about it. All right, so I've got b minus a. I didn't do anything on line 9 for that. Yeah, so I just kind of swapped some things around here. I just kind of moved that over. And then the same thing over here. I just moved the n cubed over there with the 6. Oh, and I multiplied these together. Distributed the n. So the n cubed plus 3n squared plus n divided by 6n cubed. That's what I did for line 9. Line 10, getting there. All right, so line 10, I got the limit as n goes to infinity. It really pays off. You're not going to believe how this pays off. All right, so that's b minus a. I didn't do anything for line 10. Oh, yeah, did do. All I did here was n squared divided by n squared is 1. N divided by n squared is 1 over n. Same thing here. Divide each of these by 6n cubed, so I get 1/3 plus 1 over 2n plus 1 over 6n squared. All right. So finally, the goal was to evaluate this limit as n goes to infinity. We're ready to do that now. Because look at this. It's n goes to infinity, so for line 11, n goes to infinity is not going to touch that at all. There's no n's in that. So limit as n goes to infinity is just that for that term. Now what happens as n goes to infinity to this? It was 1 over n. Well, as n goes to infinity, that goes to 0, doesn't it? So this will just be a times b minus a squared times 1. Okay? Same thing over here, b minus a cubed. That's 1 over infinity, that's 0. That's 1 over infinity, that's 0. So all that comes out of that is the 1/3. That's my limit, which looks pretty complicated, but it pays off rather nicely. Let's go on. So line 12, I've got that written there down for you, or written off for you. All right, so line 12, I just distributed that. That'll be a squared b minus a cubed. Multiply that out, so that'll be a times b squared minus 2ab plus a squared. And then 1/3 times, if you cube all that out, b minus a times b minus a times b minus a, here's what you get. B cubed minus 3ab squared plus 3a squared b minus a cubed. So line 13 and 14, where this pays off. You're not going to believe it. A squared b minus a cubed. All right, let's distribute the a there. So I have ab squared minus 2a squared b plus a cubed. Plus, distribute the 1/3 here, we'll have 1/3 b cubed. 1/3 times 3 is just 1, so that'll be minus ab squared. 1/3 times 3a squared b, well, the 1/3 and the 3 are going to cancel, that's just be a squared b. And then minus 1/3 a cubed. If you distribute the 1/3, that's what you get for the n. 14 is where it pays off. out of all this. That's a big mess, all that. Look what it comes out to be. Well, I got a minus a cubed and I got a plus a cubed. That's going to be gone. Let's see what else. All right, so I've got a squared b. Let's see, I've got a minus 2a squared b. And then I've got a plus a squared b. Well, that's 2a squared b's, and then I got a minus 2a squared b. Those are gone. We're narrowing this down quite a bit. A's b squared minus ab squared. Those are gone. All that's left is 1/3 b cubed minus 1/3 a cubed. Out of all that, that's what this integral is. Let me rewrite it. So the integral of x squared so it's a to b x squared dx. Going through the Riemann stuff, it's 1/3 b cubed minus 1/3 a cubed. Probably, if you didn't know how this worked, you would not have guessed that all that would go down to just that, but it does. But that's still not the remarkable connection. Flip over to the second page there. All right, so f of x, so forget this for a second. We'll come back to it. What's the antiderivative of that? Big F. So now we're going back to antiderivative. Remember, antiderivative is where you add the 1, makes it x cubed, and then we divide by the 3, so it's 1/3 x cubed, and I say let's let c equal 0, and I'll explain that more why we can do that in just a second. Okay, 1/3 x cubed. Now, what is f, the antiderivative evaluated at b? Well, just plug in x to be b, so it'll be 1/3 b cubed. What's the antiderivative at a? It's 1/3 a cubed. Do you see a connection between these and our answer here? It's antiderivative at b of this, because that's why I chose f of x equals x squared, because that was my function here. This is the antiderivative at b minus the antiderivative at a. That's not by coincidence. Turns out the integral from a to b, f of x dx. You just have to do the antiderivative at b minus the antiderivative at a. You don't have to go through all that. If you could figure out the antiderivative of this, it's just the antiderivative at b minus the antiderivative at a. And specifically, we can say the antiderivative of f with c equals 0. Now, a little bit of notation. In the interim, what we usually do is this. We write, so big F has an antiderivative, so we write that, and then we put the a to b kind of on square bracket there, and then we actually evaluate it like that. Okay? So here's the payoff. Payoff is this. So the integral 1 to 3 of x cubed dx. turns out, we don't have to go through that whole limit, n goes to infinity, Riemann sum stuff. This is just going to be 1/4 x to the 4th, c equals 0, because that's the antiderivative. And then evaluate that from 1 to 3. All right, so you see what I did there? I just did the antiderivative of x cubed. Then evaluate it from 1 to 3, which means plug in the 3, so it's 1/4 times 3 to the 4th, minus then plug in the 1, 1/4, 1 to the 4th. And I got this evaluated. It's almost 2. It's 81/4 minus 1/4, which is 84, which is 20. Okay. Not that hard, is it? After all. Looks bad. I mean, if you wrote it out in Riemann sums, this is an x. You know, we did the x squared one, and that took, what, 14 lines? It's not hard stuff, but busy work, I guess, I'll call it. But yeah, this is the connection. Because if you think about it, this integral is, by definition, the Riemann sum, the limit as n goes, it's a limit of Riemann sums. But it turns out the integral is equal, which is equal to a limit, is actually the antiderivative. So we've connected integrals, limits, and derivatives with antiderivative. It's the fundamental theorem of calculus. So it's big. And this is part 2, actually. Now there is a restriction. If f is continuous on AB, then the integral a to b f of x dx equals, and I'll use our little notation. I usually don't put this in it, but it's equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Yeah, f is an antiderivative. F, big F. Now the reason you can say this antiderivative here doesn't have, it's a constant of 0, you see why? Because if I put the constant plus c here, and then this would have the plus c, it would just subtract out. So that's why we can do c as 0 here. In a future integral, we may not be able to do that, but that's why we can do c equals 0, because they would just subtract out. Those constants would just subtract out. But yeah, note, this only works if f is continuous on a to b. In other words, if there's no breaks in it. So yeah, these are very easy now that we know this. So what's the integral? 0 to 3 x cubed, let's do negative 1 to 3, x cubed minus 5x plus 7 dx. Well, this is where the properties of integrals pays off, because I know separately each of these antiderivatives, and so if I can separate them, do the antiderivative of that minus the antiderivative of that plus the antiderivative. But I can do that with integrals since this is minuses and pluses. So I've got essentially three things added together. You see what I'm saying? 3 things added together. So I can do the integral of this minus the integral of that plus the integral of that. That's one of the properties. I can separate additions and subtractions. So this turns out really nicely because all I have to do is the antiderivative of that, which is 1/4 x to the 4th. Antiderivative of that, which would be minus 5/2 x squared. Antiderivative of that plus 7x. And then evaluate it from negative 1 to 3. Which means plug in the 3 first, so you have 1/4 times 3 to the fourth, minus 5 halves times 3 to the second, plus 7 times 3. And then subtract, plug in the -1, be 1/4 times -1 to the fourth, minus 5 halves times -1 squared, plus 7 times -1. And then just crank out the numbers. This is be 81/4. Let's see, that'd be minus 45 halves. Doing that quickly, but this would be minus 1/4, minus 5 halves, minus 7. Because the -1 to the fourth is positive 1, -1 squared is positive 1. So, right? And then just crank out those numbers. 81/4 minus 45 halves plus 21 minus parentheses 1/4 minus 5 halves minus 7, 28. Wouldn't guess it's been a whole number. Now, real quick. This is a good one. That's pretty good. What does this represent graphically on the graph of this? Well, if you graph y equals x cubed minus 5x plus 7, here's what you get. So what is this graphically? Well, again, the integral represents what? It's the area between the curve and the x-axis, net area. So from -1, +3, we're talking this area right here. That's what this integral is. That area is 28. Now, just to reiterate here, let me get going. X squared minus 9, integral of that, well, it's antiderivative, it'd be 1/3 x cubed minus 9x, and then evaluate that from 0 to 5. What do you got there? Well, it'd be 1/3 times 5 cubed, which is 125, minus 9 times 5 is 45. And then we like usually the ones with 0 because those usually zero out. So you got 125/3 minus 45. It's -3 1/3. Well, why is that negative? Well, look at the graph here. Y equals x squared minus 9 is this. One, two, three, 4, 5. Oops. So what area are we talking about here? Well, it's between the curve and the x-axis. So we're talking this area from 0 to 5. So it's this area here, right? It's this area and this area. Why is it negative? Well, this part's negative, this part's positive. It looks like there's more negative than there is positive because that's what the result. So this integral is that net area between the curve and the x-axis. Right? We talked about the net. It's a net area between the curve and the x-axis. Sometimes you got stuff below. All right, now, one more thing. Sorry for keeping you along here, but I didn't even mention this. All right, so negative 2 to 3 x to negative 2 dx does not equal negative x to negative 1, negative 2 to 3, which would be negative 3 to negative 1 minus negative 2 to negative 1. Does not equal that. That is the antiderivative of x to negative 2, isn't it? But why do you think I'm saying it's not equal? Why can't we do that here? Well, remember on the definition, f has to be what from A to B? Continuous. For this to work, f has to be continuous on AB. Is that true here? So f of x is x to the negative 2. That's 1 over x squared. Where is f discontinuous? It's 0, isn't it? Is x equals 0 in between those two? Yes, it is. Okay? So we can't, so f is not continuous on negative 2 to 3. It's discontinuous at x equals 0. So, yeah, you can't use this formula. It's a nice formula, but if f is not continuous from A to B fully, all the way, you can't use that antiderivative like that. So be careful with it. Most of them that we do will be okay, but you just have to watch for. If we did positive 2 to 3 x to negative 2 dx, we can do that. That would be okay, because 0 is not included there. So if we don't include the discontinuity, we can still do the antiderivative. Okay? All right.